Okay, well, thank you very much, Eric. As Eric mentioned, my name is also Eric Stellwagen, and I'm the Vice President and a co-founder of Business Forecast Systems, which is the company that creates and markets Forecast Pro. I've actually spent my entire career in forecasting. I've been doing it for over 30 years. Originally, I worked at an engineering company doing forecasting software for the electric power industry. In 1986, I left that company along with a partner, and we started Business Forecast Systems, and the first version of Forecast Pro came out in 1987. Over the years, I have worked with literally hundreds of different companies, ranging from large multinationals like Coca-Cola and Merck to small manufacturing companies, and basically all different sizes. And it's provided me with a great deal of insight into how different corporations and different organizations approach the forecasting function. This is a roadmap of how we're going to spend the next hour. Our topic, as you know, is exponential smoothing. Exponential smoothing is what is known as a time series method, a method that forecasts the future basically by extrapolating the past. And we're going to start with basically an overview where we'll discuss time series methods in general and exponential smoothing in particular. Most of today's webinar is actually going to be spent working through an example of building exponential smoothing models, really emphasizing how we approach it, how we build the models, and how we interpret the results. Again, lots of stuff to cover, and we'll see the different steps in building exponential smoothing models and using them effectively to generate forecasts. So let's get started. We're going to start with some pros and cons of exponential smoothing. One thing that people say about exponential smoothing is that it's simple to understand and it's simple to explain. And I would probably qualify that a little bit, and what I would say is it's simpler to understand and it's simpler to explain than many other statistical forecasting approaches. And the reason for that is that it models tangible components, things like sales levels, trends, seasonal patterns. And most people have a good conceptual understanding of what is a trend, what is a seasonal pattern. It's very widely accepted and used. This is absolutely true. Of the statistical forecasting methods, it is the most widely used of all of them. And it's often behind the scenes in almost any automatic approach to forecasting. I have here that it's often the most accurate. It has been a good performer in forecasting competitions. So formal academic studies that have looked at the accuracy of different time series methods have often found exponential smoothing to be ranked among the leaders. Also, just as anecdotally, I've worked with a lot of companies, and many companies have evaluated different approaches to forecasting for their own data, and there again, exponential smoothing is often a method of choice. The method is also adaptive, and what I mean by that is that as things change, as the trends change, as the seasonal patterns change, exponential smoothing is good at capturing that change and forecasting current conditions. It's robust. What does that mean? Well, what it means is that it's good at smoothing out over unusual data points. Okay, and the name sort of suggests that, exponential smoothing. But if we do have rough data, lots of noise, smoothing is often a good choice. It's easy to apply. That's true, and at the end of this webinar, I think all of us will have experienced that. It can be automated, and that's important because if we're forecasting numerous items, say that we're forecasting 1,000 different SKUs in support of, say, production, smoothing can be automated, and this can often be a good choice. So again, lots of good things about exponential smoothing. What about the not so good things? Well, it's a time series method, and as I mentioned just a moment ago, a time series method is something that forecasts based completely on the past history. So we look at the demand for, say, a given product that we're forecasting, and we're going to extrapolate it forward. That means if we have things like promotions or business interruptions, things that might move around the calendar, exponential smoothing is not going to pick that up, and it won't be a great choice for data like that. It also doesn't allow you to capture what we call explanatory variables. So let's say what I'm trying to forecast is very driven by price, and that price changes over time. So I want to use a model that can incorporate price as well as the past history of the demand. And smoothing won't let you do that. Other techniques that will allow you to bring in things like promotional schedules or explanatory variables, things like event modeling, which has been the subject of previous webinars, and dynamic regression, also the subject of previous webinars. And if you're interested in those methods, as I would encourage you to go to the archive on forecastpro.com for the webinars and maybe brush up on those topics. Another downside about exponential smoothing is that the implementation of it depends on the software developer. So implementations can vary, and there are some not so good ones. Some statistical methods are absolutely standardized in terms of how the method is supposed to be implemented. So if I build, let's say, a regression forecast using Forecast Pro, and I use it, and I build the same regression model in Excel, and I build the same regression model in SAS, I'm going to get exactly the same results, because there are absolutely standard ways of building and optimizing these models. Same thing with Box-Jenkins. If I build the same Box-Jenkins model in different applications, I should get identical results. Not so with smoothing. We're not going to go deeply into the equations behind exponential smoothing, but there are things like smoothing weights which need to be optimized, and there's not a universally accepted way of doing that. There's also, the model needs to be initialized, and that's important as well. And if you do these well, you'll get better results. And I have definitely seen some software packages that are less than optimal in the way they build these models and optimize these models, and it matters because it changes the forecasts. So I've even seen, some very expensive forecasting modules that are part and parcel of large-scale systems where shortcuts are taken, and it can make a big difference in terms of accuracy. Now, before we jump right into the exponential smoothing models, I want to get you thinking about extrapolation in general, or time series approaches in general, and in particular, one thing that's extremely important when forecasting based on the past history is data length. And the amount of data that we have that we can use for forecasting is one of the critical factors in deciding how to approach the forecasting function, and I want to get you thinking along those lines. So consider the screen right now. We're in Excel, and I'm graphing one data point. It's a little over 37,000. It's a monthly demand figure. Now consider if that's the only information that I have. So I'm using an automatic forecasting approach, say Forecast Pro, for example, and all I put in is one data point, and I say, give me a forecast. There's really nothing you can do here. Okay, how do I forecast this? Well, probably the only thing I really can do is to say, why don't we just do a straight line at 37,000? We don't have any information about things like, is it going to go up or down? Put another way, is it trended? Is it seasonal? I have no idea. All I have is one data point. So if you're using an automatic approach and you have very few data points, you really need to keep this in mind. An automatic approach is going to require some data. And in general, extrapolation is going to require some data. So let's get some more data. Okay, now we have 3 data points. The first one seems to be around 37,000, maybe a little bit more. The second one's a little less than that, and it goes up a little bit on the third point. So we have 3 months worth of data, and we're still extremely limited in how we can approach this. Probably the only reasonable thing to do would be to average them. And we'd end up with a flat line forecast right about here. Is that going to be a good forecast? Probably not. Okay? But if all we're doing is looking at the data, and that's what software does. It knows nothing about the data, and if we're using an automatic approach and all we're providing is 3 months, then we're going to get a very simplistic forecast. So let's get some more data. Now we have 12 months, and things are a little more interesting. We can see that the data go up and down. So is it going up and down because it's seasonal? Or are we just selling a certain amount and maybe fluctuating around that amount? We really don't know, because we only have 12 data points, and it being monthly data, we don't have the opportunity to look and say, how did the different months, how do they correspond from year to year? With only 12 data points, we really can't get at the seasonal pattern, if there is one. So what do? Well, I guess we ask ourselves, are the data trended? Should I be forecasting that maybe this is going down or going up? Or should we have it be flat? And with 12 data points, that can be a little challenging. If I were to take out a ruler and do a best fit line or maybe run a regression on time, I'd probably find a little bit of a downward trend to this, and perhaps I'd forecast a small downward trend. But again, without a lot of data, very hard to know how to proceed. And of course, that's the point. So let's get a little more data. Now we have 2 years worth. And now when we say things like, well, is it trended? Not really. It's pretty flat. So we're starting to get a little more comfortable with the trend. Is it seasonal? Yes, it is. And if we start to look, we can notice that like this trough here and this trough here, those are both Decembers. And January seems to go up, and November seems to, compared to December, go up as well. So we can start to see a pattern that's repeating itself. It's not perfect, but it's definitely there. And if we had the ability, I could do this, but it will take a time, which I'm not going to do. If I put it year over year, it would be even easier to see the seasonal pattern. But it's pretty clear to me the data are not trended, so I'd probably forecast going forward a non-trended forecast. But they are seasonal, so I would superimpose a seasonal pattern on the non-trended forecast. And that's actually a type of exponential smoothing. So the exponential smoothing really revolves around different ways of forecasting trends and seasonal patterns. And in this case, I would say it's not trended, but it is seasonal. Let's get some more data. Okay, we have 3 years worth of data now. And keep in mind, for a lot of people, 3 years is a lot of data. There are many products where the entire product life cycle is less than 3 years. What do we see? Well, something happened here. So we were selling, we thought it was pretty flat when we were looking at 2 years, but it's increased. And I guess my question is did it shift? Were we selling around this level and now we're jumped and we're up here? So you might call that a level shift. Or is this some sort of emerging trend where there's really some upward movement and we should continue that upward movement into the forecast? So now we have 3 years worth of data. Things are getting more clear, but on the other hand, they're not super clear. Okay, there's still some challenges, and this is real data. What if we get some more data? Okay, now we have 6 years worth of data, and things are very clear now and easy. Are the data trended? Oh yeah, absolutely. You can see a strong trend in the data. It was a little slower in the beginning, but then it really picked up. So we had a changing trend, but there's definitely an established trend in this data set. Are the data seasonal? Oh, absolutely. Very easy to see things like these troughs and the repetitive patterns in some of the peaks and valleys. So yes, now that we've got 6 years worth of data, everything's easy. We can easily tell whether things are trended and seasonal, and that's of course the point of the exercise, is that with enough data we can really understand the components of the data and know how to proceed. Exponential smoothing revolves around 3 central components. One is the level. So think of like a sales level and how the level changes in time. Another component is trend. and the third component is seasonal pattern. And when we think about smoothing, we might notice that, like, let's take the trend. The trends here are changing. So the trend in the beginning of the data is different than the trend in the middle or perhaps at the end. And the other components, the level and the seasonal pattern, they can be changing as well. And one of the strengths of exponential smoothing, as mentioned in the pros slide that I put up earlier, is that it's adaptive. So it's going to capture how things are changing, and it's going to capture what we call final values. What is the trend at the end of the data set? What is the seasonal pattern at the end of the data set? What's the sales level at the end of the data set? And it's going to use those final values, if you will, of those components to generate a forecast. So these are what we're thinking about when we're thinking about smoothing: our levels, trends, seasonal patterns, and how they change in time. Keeping in mind, this was a very unfair exercise. I did not tell you anything about the data. Now, what is this data set? Because we're going to use this data set as our primary example. It actually comes from a telephone company, and it is what they call connection data, but it's when the phone company comes out and actually installs phone lines. So it's the number of installations on a monthly basis. Decembers are low because they don't install as many phone lines in December as they do in other months. And in general, each month has a pattern to it. So it's a pretty seasonal data set. If I worked for this phone company, I could probably tell you why it was flat in this section and picked up. So again, with knowledge of the data, this series will make more sense. And even if, let's say we only had 1 month worth of data, okay? So I want to make a forecast. I have 1 month worth of data, but I know it's connection data. I know it's the installations, and I work for the phone company. And if somebody said, is it seasonal? I'd say, yes, it is. I'm not saying that from the graph. The graph I can't tell. What I'm saying, the reason I can state that is that my knowledge of the data, connection data, is seasonal. We connect fewer phones in December than other months, for example. So with knowledge of the data, there's more that I could do with limited data. And so even with 12 months, if I have no knowledge of the data, I can't really answer questions like, are the data seasonal, are they trended? But perhaps if I know what I'm working with, then I could, and that might impact the approach. With lots of data, then everything's easy. And my knowledge of the data is still useful, but automatic methods and techniques like exponential smoothing will work quite well because I've got enough data to answer those questions from the data directly. Okay, so again, a fairly important point. Let's go back to our slides for a minute and talk about exponential smoothing. Well, one thing about smoothing is it's really not a single method, it's a family of models. And basically, it models, as I mentioned, 3 different components: level, trend, and seasonal pattern. And the models that compose the model family consist of different ways of forecasting these 3 components, different ways of forecasting trends, different ways of forecasting seasonal patterns. The model assumes that each of these components is changing, okay? So that over time, the sales levels, the trends, the seasonal patterns are all changing. It assumes that there's also random variation. We sometimes refer to this as noise. But essentially that there's some random component to the data, and that's part of what we're trying to understand. The model uses something called smoothing weights. And the concept here is that if you have something that's changing in time, so I know that the trends, for example, is changing in time. How do I forecast something that's changing in time? Well, if I need to forecast something that's changing in time, I want to give more emphasis to recent history, because the recent history will reflect the current conditions because things are changing. On the other hand, if I know that there's some random variation, then I don't want to just emphasize the recent history. I want to sort of go back and do a lot of what you might call smoothing. I want to do a bunch of averaging, for instance, so that I can get at those underlying trends and seasonal patterns. And this is what exponential smoothing is all about. It's the concept of there's an advantage to emphasizing recent history, and the advantage is you capture change. And there's an advantage to doing looking over a lot of history. And the advantage is that by looking over a lot of history, you reduce the impact of the random variation. Exponential smoothing is designed to balance these two things, and the smoothing weights are what controls the balance. So we'll see how this works in a minute, but it's really the key to the model. After we have decided how much data to use to estimate each component, we can calculate what is the level at the end of the data set, what is the trend at the end of the data set, what is the seasonal pattern at the end of the data set. We refer to these estimates of conditions at the end of the data set as final values. So the final value for the level, and the final value for the trend, and the final value for the seasonal pattern tell us the conditions at the end of the data set, and these are what the method uses to generate the forecasts. Now, before we launch into our example, we're going to consider the different members of what we call the Holt-Winters exponential smoothing family. So I mentioned exponential smoothing is really not just a single model, it's a bunch of models. There are 12 models depicted on this slide, and what they come down to is really 4 different ways of extrapolating a trend. These are all pictures of forecasts. And in this first column, we have 4 different ways of extrapolating a trend. We could say it's not trended, so it'll be a flat line. We could say there's a linear trend or a straight line trend, and we'll forecast a straight line trend either going up or down. Damp trend is another option. A damp trend is a trend that starts off linear but fades out or dies out over time. And an exponential trend is also an option. That's a trend that grows as a percentage of itself, and at times can have very explosive growth. But essentially, the Holt-Winters family of exponential smoothing models incorporate 4 different ways of extrapolating a trend. It also incorporates 3 different ways of extrapolating a seasonal pattern. The first column are non-seasonal, so that's one option. The second is what we call additive seasonality, and the third is what we call multiplicative seasonality. An additive seasonal pattern is one where the seasonal variation is assumed to be constant. So we're going to add on a certain amount for the fact it's December, or subtract off a certain amount for the fact it's February, that kind of thing. And you can sort of see the seasonal pattern is uniform in the forecast period. The alternative, which is more common, is what's called a multiplicative seasonal pattern. And this is where the seasonality can be thought of as a percentage. So in December's, let's say it's a good month, we're selling toys, for instance. In December, we sell 20% more than a typical month. And 20%, if we're trended upwards, gets to be a bigger and bigger adjustment as the underlying level increases. So you can sort of see the fanning out of the peak to trough here. It gets bigger as we go forward. And that's indicative of a multiplicative seasonal pattern. So again, when we talk about exponential smoothing, there are actually many different types, and there are many that are not part of the Holt-Winters family. So you may have heard of things like single exponential smoothing, or Brown's exponential smoothing, or triple exponential smoothing, or adaptive response rate exponential smoothing. There was a very good article by Everett Gardner, who is a leading authority on exponential smoothing models. It was in the International Journal of Forecasting a while back, where he surveyed different approaches to exponential smoothing and made a very strong case that the 12 on the screen are the ones to concentrate on. And very often I concur with that. The Holt-Winters family, as they're known, is really, I think, the most useful of the smoothing models. And they're the ones that we implement in Forecast Pro and the ones we'll be talking about during today's webinar. Now, some of these models have names. And so you might hear people talk about simple exponential smoothing or Holt or Winters. And simple is actually one of the models here. It's the one that's not trended and not seasonal. Holt is a model that's not seasonal but is trended, and the trend is linear. And finally, Winters is trended with a linear trend and a multiplicative seasonal pattern. So people will refer, they'll say things like, oh, I'm using Holt Winters exponential smoothing. What they're referring to is actually all of these models. When you actually build a forecast, you'll use a specific one. And again, these three have names. You'll find them used in the literature, and those are the ones that are being referred to. All of the models can be identified using two letters. And this is a little nomenclature that you will find in forecasting textbooks. You'll find it in forecasting software, and we do use it in Forecast Pro. But the two letters tell me what type of trend and what type of seasonal pattern. So the first one is for the trend, and the options are N for not trended, L for linear, D for damped, or E for exponential. The second letter is for the seasonal pattern, N for not seasonal, A for additive, or M for multiplicative. So if somebody says, I used an LA model, then it would be this one. They used a model that had a linear trend and an additive seasonal pattern. If they said they used an NM model, it would be this one. Not trended, multiplicative seasonal pattern. But one step in building a smoothing model is deciding which of these 12 models is appropriate. Usually that's done a couple of different ways. Sometimes you just know it. If I know the data are seasonal, I can eliminate the non-seasonal options. If I know they're trended, I can get rid of some more. So usually it's pretty straightforward. There's also automatic ways of doing it, but we'll be looking at this. So how do I determine the type of trend and seasonal pattern? Again, one thing I could use is my own knowledge of the data. Another thing I could do is look at a graph. And if I have enough data, sometimes it's pretty obvious. And a third way I could do that is with some sort of an automatic algorithm. And Forecast Pro has automatic algorithms built into the software. And what I'll say about the automatic algorithms is they work well if you have enough data. So the real problem with automatic algorithms is that they require enough data so that the statistics of the data are clear. Okay, so at this point let's actually look at an example. And the example is going to be the same data set that we looked at before here, which is our installation data. Okay, so we looked at this in Excel, but again, let's think now in terms of our exponential smoothing components. First of all, is it trended? Yes, absolutely. We have a strong trend, and we fully expect to be forecasting that trend to continue. Is it seasonal? Absolutely. We've noticed that Decembers, for example, are consistently these trough months. Okay, and if we did want to look, say, year over year, let's do that. Let's put a few years on it. We can see this pattern where, for the most part, these lines are moving up and down together, and certainly in this area of the data that's very clear. But there's definitely, it's not perfect, but there's definitely a seasonal pattern here. So we're pretty comfortable. Let's go back to our slide for a second. And we're saying, okay, well, it is trended, so we can wipe out these three options, the non-trended ones. It is seasonal, so we can wipe out these. And from 12 models, we're down to 6. And now the question is, we know it's seasonal. What type of seasonal pattern, what type of trend? The trend, certainly towards the end of the data, is pretty consistent going upwards, and I think I'd use a linear trend for this. And linear trend is the most common type of trend to use, so I'm pretty comfortable with that. What about the seasonal pattern, this additive versus multiplicative? What we tend to look for is the peak to trough variation. And the question is, are the peak to troughs increasing as the data increase. This is a little ambiguous with this example, but I'd say for the most part, probably. So this is a tough one. But I think if I were forced to choose, which we are, I would say let's use a linear trend and a multiplicative seasonal pattern. So I'd probably end up with this model, which is the Winters model, also known as an LM model, a model with a linear trend and a multiplicative seasonal pattern. Okay, so let's go ahead and forecast it. Here's the forecast, and you can see it's extrapolating that linear trend, and it's also extrapolating a seasonal pattern. What model did it select? We let the program decide here. And it actually chose a linear trend and an additive seasonal pattern. Okay? And again, I said it was pretty ambiguous as to which one for the seasonal pattern, but I would have probably visually come to a multiplicative pattern. The software looking at it statistically came up with an additive pattern. Now what I want to start to do though is to look at the two different parts of this model. One is the smoothing weights. These are weights or numbers that go into the equations. We're not really going to go deeply into any equations in this webinar, but if you are interested, you could consult the Statistical Reference Manual in Forecast Pro. You could also consult any textbook on forecasting. They all will have one or more chapters on exponential smoothing, and they'll all explain the different approaches and the role of the smoothing weights. But basically, they take on values ranging between 0 and 1, and the closer they are to 0, the more smoothing they enforce, the more data they use to get at the underlying component. So the level is 0.03. That's a very small value. So it's doing a lot of smoothing. The trend, on the other hand, is 0.99. Again, they go between 0 and 1. So this is a very large value. And it's saying for the trend, I'm really going to concentrate on the recent history. The seasonal pattern, 0.24, that's a moderate value. And so we'll be doing some smoothing, but certainly not as much as we were doing for the level. So the smoothing weights control the amount of smoothing that goes on. They vary between 0 and 1. They don't have a lot of direct interpretation, other than if they're close to 1, then they're very adaptive and concentrate on the recent history. If they're closer to 0, then they're enforcing more smoothing. Once we have them, though, we can put them into the equations and get the final values. And those are these shown here, and these are important. These are what the forecasts are made of. So the sales level at the end of the data is 65,782. That's the starting point for the forecast. The trend at the end of the data is 742 units per month. So if we start here and increase by 742 units by month, that tells us the trend. The seasonal pattern is additive, and each month, January, February, March, April, May, June, etc., each month has an index which is either positive or negative. And in an additive model, these would either be added or subtracted from that linear trend forecast to introduce the seasonal pattern. We'll see this on a slide in a minute. Let's say that the model had been multiplicative, and what I'm actually going to do is to select, to choose the model explicitly rather than letting Forecast Pro decide. I'll go into exponential smoothing. I'll choose custom, and the custom option allows me to specify any type of trend I want. I can say it's not trended, so it will forecast as a flat line trend, or automatic. Let Forecast Pro decide on what type of trend to use. Or linear, that's what we want. Or damped or exponential. But I'll leave it at linear for this example. The seasonal pattern, I also have control over. I could say it's not seasonal, or I could say let's do it automatically. Let Forecast Pro decide on what type of seasonal pattern. Or choose additive or multiplicative. I'm going to choose multiplicative just to show you how a multiplicative model works. So I'll go ahead and accept that. Here's the new forecast. If you were watching, it did change a little bit. And here's the new report. And if I scroll down, you'll see I've got a linear trend model with a multiplicative seasonal pattern. It still has 3 smoothing weights: level, trend, seasonal. And the final values are shown here. The final values are similar but different. So the level is still around 65,000. The trend here is now 780 units a month. But what's changed is the seasonal indices. These are now multiplicative, meaning that they're multiplied into the underlying trend to introduce the seasonal pattern. There are 12 of them, one for each month. And you might notice that our largest one is right here for March. The value is 1.08. If I multiply something by 1.08, I increase it by 8%. And so the interpretation here is that March is a strong month in terms of the seasonal pattern, and we sell about 8% more in March than we would in an average month. If we look for the lowest value, it's here in December, 0.81. If I multiply something by 0.81, I lower it by 19%. So December is our weakest month, and our sales are down about 19% in December. And we commented again, this is installation data, and that's the reason for that. So let's go and fill in some details on the slides here, but we've been working through it in the example. The smoothing weights are important. They take on values between 0 and 1. The larger the value, the more emphasis on recent history. A best practice is to optimize the weights to minimize the fitted error. So the best thing to do, and this is good news for forecasters, is to automatically determine what the smoothing weights should be by fitting them to the data. Some implementations might use a single weight for different components. So methods like double and triple exponential smoothing will constrain that the smoothing weights be the same for the level and the trend and the seasonal pattern. And this really should be avoided. It's done because it's easier to optimize the model and quicker to optimize the model. But particularly for like our example where we had the level be a very small value, the trend be a very large value, constraining them to be equal would really hurt the forecast. And this is what I meant when I said implementations vary and some are poor. So in general, we don't want to set them to standard values. We don't want to restrict them to be equal to each other. And we don't want to restrict them to narrow ranges. And you will find this in some software packages, so you need to be careful. Constructing the forecasts. This is the role of the final values. Now I walked through it on the screen, but let's see how it works here. So for the first forecast, I'm going to start at the level, okay, which in this case was 65,870. That's the final value of the level. I'm going to add a trend, which is 779, so the final value for the trend. And because the first forecast point happens to be June, I'm going to multiply by June's index, okay, which is over here at 1.03. And if I do the arithmetic, I get a forecast of 68,682, which matches our forecast here on the screen. If I want to forecast 2 periods ahead, I start at the level, but now I'll add 2 trends because I'm going 2 months forward, and then multiply by July because our second forecast point is July, and that'll give me my second forecast. So the construction of the forecast is very straightforward. It uses the final values. It starts at the final value of the level, and it implements the trend, and then in this case, because it's multiplicative, it multiplies in the seasonal pattern. But again, a very, very straightforward way of doing this. Now, we're nearing the end of our presentation. We will be having time for questions, and just as a reminder, if you haven't been sending in questions and you want to ask some, be sure to send them in using the chat box. But before we take questions, I'm going to talk a little bit about a brand new model which we actually developed here at Business Forecast Systems, and which is implemented in Forecast Pro, and we call it the NA Constant Level Model. Not a very sexy name, but I'll show you why it's called that. Basically, there are certain types of data where we noticed exponential smoothing was not doing a very good job. And in particular, it was data that has what you might call a selling season. That there are certain times of the year where there are significant sales, and then there are other times where there are not. So think of things like snow shovels. We don't sell a lot of them in the summer. Or flu vaccines. Again, it's only certain times of years, or certain times of the year rather, where these are going to come into play. Now, the model, let's do this by example, Here's some data that comes from agricultural chemicals. So it's things like pesticides and growth products for agriculture. It's weekly data, okay? And it's real data, and it's very low level. But here's a good example. This product really is only applied at a certain time of the year. Okay, so it's a certain type of pesticide, and evidently there's only certain times of the year where probably the pest is available to be eradicated. So we have these months, and they occur at similar times from year to year, but not exactly the same time, where we're going to apply it. And when it's not that time of year, we basically don't sell anything. And again, we have other types of pesticides, and some of them have similar patterns. But this is the kind of data where you might say there's a selling season. These are the growth agents, so there's only certain times of the year where we're going to be applying the growth agents. Let's concentrate on this one. Now, if I forecast this, and I'll go ahead and do that. And here's my forecast, and it looks pretty reasonable. And if I look into my forecast report, what you're going to see is that it's using what we call exponential smoothing. It's NA, no trend, additive seasonal pattern. So certainly the data weren't trended, and we're using an additive pattern to get the seasonality, so that everything's fine. But it's also using a constant level. And what the constant level model does is it sets the smoothing weight to something very low, 0.0001. And then it optimizes the other weight, the seasonal pattern. And basically what it's saying is the level's not changing. And it's designed for this type of data. And it is a model, so it's a very straightforward model. It's simply a type of an NA model. But it's one where the smoothing weight for the level has been set to essentially something close to zero. And the reason is because what we're really looking at is not how the level's changing. It's not changing. And that wasn't part of the Holt-Winters family. If we didn't do this, if we said, look, what if we just used a regular NA model? So I'll go into custom, I'll say not trended, additive seasonal pattern. And here's the forecast. And you can see it's pretty disastrous. And what happens to understand this, and I'm not going to go into great detail, if people are interested in some more detail, you can contact me and I'll explain it. But in a nutshell here, if we look at what's called the fitted values, which is how we track the data, this model actually fits the data quite well. And you can see it really kind of captures the pattern. Although if you look closely, it's kind of like it's shifted to the right. And what it's doing is saying, I'm forecasting the next point to be very similar to the last one. And by doing that, it can really kind of capture the big jumps and only miss them for the first week in this case. But notice that it's at the expense of understanding the actual seasonal pattern. And so if I were doing a standard approach to smoothing, this is probably the model I would build because it fits the data better. So if I look at something like, let's say the root mean squared error, or the MAD, let's use the MAD, 7.65. If I look at that, this is the model I'm going to get. On the other hand, I'm going to remove that. If I use this constant level model, it doesn't fit nearly as well. You can see it really misses a lot of this stuff. On the other hand, it forecasts much better. And if I look down at the MAD, it's much higher, 15. So this is not a model you would find if all you were doing is fitting the smoothing weights to the model. But it is a model that logically should be used when you have data like this. And so we've devised specialized tests to determine when it's useful and to apply it. And again, we implemented this actually in the latest release of Forecast Pro Track, so in version 4. And it works extremely well, and it pops up quite a bit actually. So it's a variation of the NA exponential smoothing model, whereby the smoothing weight for the level is set to 0.001 and the seasonal weight is optimized. So it's not rocket science, but it is useful. We've put in logic so that Forecast Pro can automatically determine when the model should be applied, and that logic works very well. And as far as I know, it's unique to Forecast Pro. That probably won't remain the case for long. Usually when we come up with a better mousetrap, it tends to be implemented elsewhere as well. But I think, again, for people that have this type of data, where there are certain times of the year where we're selling, this is a very useful technique. Okay, so to summarize a little bit, exponential smoothing is a very useful time series method. It's easy to apply it, and it can be done either interactively or automatically, and it's generally pretty easy to understand and explain to people because it works with components like level, trend, and seasonal patterns. It's adaptive. As these components change, as the trends change, as the seasonal patterns change, exponential smoothing will adapt to that change, and the forecast will reflect the final level, the final trend, the final seasonal pattern. So they'll reflect current conditions. Now, because we are extrapolating current conditions, it's best used for short-term forecasting. Obvious question, what's short-term? Well, I would say for monthly data, most exponential smoothing models are probably used in sort of the 12 to 18 month looking forward. That's a reasonable definition of short-term. I wouldn't use it for a 5-year forecast or a 10-year forecast because the extrapolation of the trend is too simple. Okay, so we're going to take some questions. I know that people have been sending them in because I can tell from the other people in the room with me. But before we do, I want to just mention that we've been using Forecast Pro, actually Forecast Pro Track, during this webinar. And if you want to learn more about Forecast Pro, we'd love to tell you more about it. And one thing you can do, actually, in the chat box, if you want, is just let us know you're interested in getting a demo. It's free. We do them via WebEx, and so you can talk to one of our knowledgeable salespeople here, and they will walk you through the product and its capabilities and be happy to show you everything it can do. There's also a lot of information on our website, forecastpro.com, and so I'd encourage you to go there. As I mentioned, there's also a lot of educational materials there too. We've got an archive for webinars we've given in the past, which you can simply run on demand. We've got links to our blog and our YouTube page, and a lot of course, a lot of product information as well. But if you want to learn more, let us know, visit our website, or give us a call, and we'd be happy to tell you more. In addition to forecasting software, VFS does offer forecasting seminars, obviously webinars. We also do product training workshops. We can work on site. We can do them remotely via WebEx. So if you do have needs in these areas, let us know. And again, our website is the place to start if you want to learn more. We also do have a blog called The Forecast Pro, and it's full of educational articles and blog posts on topics of interest to business forecasters. So I'd encourage you to check that out. Okay, so at this point we're going to open it up to some questions. And what do we have for questions, Eric?
All right, we got a bunch. Let's see how many we can get to. We'll start with this one. Can you review the level component and maybe comment on, for example, how does a simple exponential smoothing model differ from just a moving average?
Okay, excellent question. So let's see. The example that I've been using, the level is actually, because it's trended, the level's not as important. But consider a data set where, let's say the data really all look like this. Okay? Actually, I know a better one. Let's go back to our spreadsheet. Let's say this is our data set, and what we're really interested in knowing is the level, the underlying level. So the concept is we're selling a certain amount, and that level might change in time. And so maybe this level drifted upwards, and maybe now we're selling here, and we want our forecast to be over here. So the level is similar in some ways to a moving average, but it's a more sophisticated one. In terms of a moving average, let's say I do a 24-month moving average. I'm going to take the last 2 years, average them, and I'll be down here somewhere. Whereas smoothing, what it would do, it's a weighted moving average in terms of the level, and it would give more emphasis to this point than to that point, and more emphasis to that second to last point than the third to last point, etc. So the weights actually go down. They decrease exponentially, which is where the exponential smoothing name comes from. But it's fair enough to think of simple exponential smoothing as a form of a moving average with weights, where the weights decrease the further back you go. For details, you can go to, again, any textbook on smoothing or to the Forecast Pro Statistical Reference Manual, but that's basically how it works.
Okay, thanks, Eric. Here's one we got from more than one person. Can you comment on Box-Jenkins or RIMA versus exponential smoothing? What are the differences, and how might you know when to use one versus the other?
Okay, another good question. So we've been concentrating on this webinar. We've been talking about exponential smoothing models. Box-Jenkins, also known as a RIMA, is another statistical forecasting method. And if we look at just univariate ARIMA models, then it's very similar to smoothing in many ways. There are a couple of differences, though, and one is that Box-Jenkins models, first of all, in terms of theory, they're all linear models, and the structure, they're not based on components like level, trend, seasonal patterns. They're based on correlations in time, so that from a theoretical point of view, they're very different. From a practical point of view, there are certain types of data where Box-Jenkins will yield better, more accurate forecasts than smoothing. And there are other types where smoothing will actually yield better than Box-Jenkins. In one famous statistical study, the M2 competition, it was shown that exponential smoothing was better than Box-Jenkins about 55% of the time. But if we think about that, that says Box-Jenkins was better 45% of the time. So that's actually a pretty even split. In terms of how do you tell when to use one over the other? Box-Jenkins will work better for longer, more stable data sets with less noise. So smoothing is good at smoothing out over rough data. Forecast Pro uses something called expert selection, and that actually it uses an out-of-sample test. It can try both of these methods and look at performance, and that's another way of doing it. So again, if you're using Forecast Pro, the expert selection will do this for you. If you're using a different application, then constructing a test might do it, or in general, where you have noisy data or things are changing rapidly, use more exponential smoothing. Where you have long stable data sets, consider Box-Jenkins.
Okay. How would you suggest handling quote-unquote seasonality that is really only caused by a 4-4-5 calendar when using monthly buckets of history?
Okay, a fairly specific question there. 4-4-5 calendars, for those who aren't familiar with them, refers to what I call a production calendar. So that rather than using the actual calendar month, what we're going to say is we're going to have 12 production periods per year, and each one will have either 4 complete weeks or 5 complete weeks. And this introduces a problem. The problem is that the periods with 5 weeks have a lot more demand than the periods for 4 weeks. And as the question poser has mentioned here, in his case or her case, it's not due to seasonality in the data, it's just due to the fact that they're collecting the data as either 4 or 5 weeks. How do we approach that? Probably the simplest way is to use what's called a weighting transformation. This is built into Forecast Pro. It's also very simple to do in something like Excel. But what you would do is to take your 4-4-5 data and divide through by the number of weeks. This will transform the data. It will convert it from 4-4-5 to essentially an observation of sales per week for each period. So it removes the 4-4-5 nature from the data. Forecast that, and then after you've done so, multiply back in whether it's going to be 4s or 5s in the forecast period. So if you're using Forecast Pro, that's under what we call a weighting transformation, and it's actually, you can see here it's grayed out because I don't have one set up for this data, but it's built right into the product. If you're not using Forecast Pro, it's a very simple transformation where we divide through by the number of weeks in the period, either 4 or 5. We forecast the resultant series, And then to get our final forecast, we take out a calendar, we determine whether the future is going to have 4 or 5 weeks in each period, and we multiply it back in.
Okay, and let's do one more question. How do you account for, or how do random zeros in history affect the model, and how might you account for them?
Okay. So now the question is random observations of zeros. So this would be, for example, let's say low volume data, say spare parts or something like that, where we might encounter a lot of zero demand periods. First of all, if you have zero demand periods in the data, one of the things you really want to understand and be sure of is, are they indeed zero? So let me, this data, for example, has plenty of periods that are zero, and they're real. It wasn't a stock out, it wasn't a problem, it was the fact that nobody bought anything during those periods. There was no demand. So how do we treat this? In this case, it's part of the seasonal pattern, and we'll capture it as part of the seasonal pattern. In the case of random ones, where it's low volume, sometimes it's zero, it will tend to have us use a method, like for example the Croston's intermittent demand model, that's designed for data that has frequent zero demand periods. But again, what I would say is the following, which is step one, make sure that the zeros are truly zero, that it's not something like a stock out, which might be forecasted differently. It's not something like a data problem where the data just wasn't collected properly. But if that's not the case, then what you want to do is use a model that's appropriate for why the zeros are there. And if the zeros are there because it's low volume, then we would use a low volume model like the Crostons or maybe some of the discrete data models. And if it's there because it's part of the seasonal pattern, then again you might use something like the one we used in this example. Okay, so let me just say the following, which is thank you for joining us this afternoon or whatever time it is in your part of the world. We actually had over 400 people sign up for the webinar and from 45 different countries, so a nice international mix today. This is a quarterly webinar series, so next quarter we'll have another live one. You'll all be notified of that, and I'd encourage you to attend. I think our speaker is going to be from Oliver White, and we're still putting together the exact topic, but that should be good. Their speakers tend to be very knowledgeable, and I always learn something from it. As Eric mentioned, you'll be receiving an email sometime next week when we've posted the webinar for on-demand viewing, and I hope everyone enjoyed themselves and maybe perhaps learned a thing or two, and look forward to seeing you, so to speak, again at another webinar. So thanks again.